Now, this is a course on statistical physics. Statistical physics is the study of the average property of a large number of things. Now, those things can be anything. For example, population, financial market. But the most successful application is in the system of atoms, the theory of matter, where it was first developed and most successful. Of course, it is the dream of economists and everybody to reproduce that success in economics and in financial markets and so forth. And so far, I don't think that has happened. So I think if we study the atoms system in which we know everything, if we learn from that, we may be able to make some progress in those more difficult problems like population, financial markets, and maybe world history, things like that. So we will concentrate this lecture on a system of atoms. By atom, I mean just a unit of things, and that includes a molecule. I just use the term atom to express a unit of thing. The success of the application of atoms depends on the fact that all atoms are identical, and that we have very good experiments on them. So that in the history of physics, in the study of the first day is thermodynamics. Which is a phenomenological theory of matter. By phenomenological, one means that it is not based on the microscopic mechanics, but just based on a construct from the facts. And it's very successful, as you know. And then another topic is kinetic theory. This theory is based on the property of atoms according to classical mechanics. So it's a microscopic theory. Of the approach to equilibrium. See, from experience, we know that if you leave a system of atoms alone, it will very quickly reach a steady state. That's called equilibrium. And the kinetic theory is a study of how the system approaches that state. And then it comes, and this is most successful in the theory of gases, which we'll talk about. And then there's statistical mechanics. Which is the microscopic theory of equilibrium. It is a study of the equilibrium state, but it's very general. It's not confined to gases. And so these are the main subjects. And in this lecture, I will assume that you have had some thermodynamics. So I'll just skip that. So we'll start from here and here. And then after that, I think I would like to discuss the case of Brownian motion as an example. And the thing is the Langevin equation. I'd like to discuss it. And then if we have time, I guess we'll discuss it in a leisurely pace. And if we have time, we'll assess the theory of the order parameter, which is a new kind of phenomenology. So we'll start on kinetic theory now. Now, what is kinetic theory? Our subject of study is a system of atoms. Atoms. And this includes molecules. It's just a unit of the system. And first I'd like to remind you of some properties of atoms. a very important number is Avogadro's number. And if you take a system of atoms, as we observe it at the standard temperature and pressure, STP, standard temperature and pressure. That means 300 degrees Kelvin and 1 atmosphere, which is room temperature and under the atmosphere. Under this condition, from chemistry, we know that there is something called a gram mole, 1 gram mole. That means the gram equivalent of the atomic number of the substance. For example, for hydrogen, for H2, is 2 grams. For oxygen, it's 16 grams. And for nitrogen, it is 28 grams. Each of these is called 1 mole, 1 gram mole. And that gram mole shares many standard properties, right? Each gram mole contains how many atoms? Each gram mole contains Avogadro's number, our number of atoms. A. And this number, as you know, is 6.02 times 10 to the 23. And that's a lot of atoms in 1 gram mole. That is, in 2 grams of hydrogen, or 16 grams of oxygen, 28 grams of, they each contain 6.02 times 10 to the 3rd units of these things. And under standard temperature and pressure, they occupy the molar volume occupies molar volume, which is 22.4 liters. Is it 22? Let me check. 22.4 liters, or 2.24 times 10 to the 4th cc. 2.24 times 10 to the 4th cc. Now, how much is that? That's about a cube, about 28 centimeters across. 28 centimeters. So it's about this big. Huh? So, and that contains 10 to the 23rd atoms. So there's a lot of atoms. So if you take the so the density n of atoms, the density is equal to the number of atoms divided by the volume. So it's Avogadro's number, 6.02 times 10 to the 23rd divided by 2.24 times 10 to the 4th, and you get about 10 to the 19th. About 3 times 10 to the 19th. Per centimeter cube. That means in 1 centimeter, who's about this big, right? That contains 10 to the 19th atoms. And that's why we can do statistics, because there are lots and lots of atoms. I think I should first move this here so I can. Now, we are talking about atoms at the room temperature. So they will be classical mechanics. But as you know, fundamentally, they will be quantum mechanics. Under what condition can you treat them by classical mechanics? So let me remind you. In quantum mechanics, there's something called the de Broglie wavelength. The de Broglie wavelength is the length in which you can localize an atom. So that if you consider an atom in a classical limit, it is a wave packet. And the extent is of the order of the de Broglie wavelength with lambda, and is equal to Planck's constant divided by the momentum. So if you have a bunch of atoms under standard conditions, what you see is a bunch of wave packets. But they're so tight that you don't recognize them. And they had better not overlap. So this is the Broglie wavelength. And the separation, say, is R0. So R0 had better be much greater than the Broglie wavelength. Otherwise, you have to use quantum mechanics. And how do you translate this condition into temperature and density and such? Well, you see that there's something called a thermal wavelength. Now, the thermal wavelength is the Broglie wavelength of an atom with a typical momentum in a gas. Lambda thermal is equal to h bar over 2m times the average energy of an atom in a gas. And just to use a factor you might know, the energy is of the order of the Boltzmann constant times the temperature. And so the condition for classical mechanics to be valid is that the thermal wavelength must be much less than the average atomic separation, which is proportional to the density to the minus 1/3 power. So then you can substitute in some of the quantities, you obtain, or you can write this as lambda thermal times n cubed. Lambda cubed times n is much less than 1. And lambda cubed n is, I write this as, this could be written as 2 pi h bar. We like to use h bar instead of h, so h is equal to 2 pi h bar. So it'll be like q times n divided by the square root of 2m Boltzmann constant times t. This must be much less than 1. Here the thermodynamic quantities, the density and the temperature. And this relation sets up a condition on the if you construct the Tn plane. Here's the temperature, here's the density. This condition is a line like this. And then in this region is classical. Fine, this is classical. And here is quantum. And of course, this line is not a sharp dividing line. It just gradually goes from quantum to classical. But we better make sure that our region is way safely out in this corner. Otherwise, we have to use quantum mechanics. So now, having decided that we can treat our system with classical mechanics, we have to review how classical mechanics describes an atom. And this I'm sure everybody knows. What is the essence of classical mechanics? It's Newtonian mechanics. This is classical of a point mass. We treat that as a point mass. The first thing you know is that in classical mechanics, the state of a point mass is specified with two numbers, the position and the momentum. Each one is a vector, so there's really 6 numbers. So each atom is described by its position, let's call it x, x momentum, and of course at a certain time t. So that if you want to know the state of a atom, you can represent it in a phase space. This phase space is a 6-dimensional space with p here and x here. It's very, I cannot really draw it, but this represents 3 axes. So it's just 6 axes perpendicular to each other, and each point here is one atom. At a certain time, this atom has this position, has momentum, and as time goes on, it moves. And Newtonian mechanics describes the trajectory of this particle in this phase space. Since I'm considering a gas of atoms, I don't have just one, I have a large number of atoms, 10 to the 19 in 1 cc. So in my system really consists of a lot of points. It's a cloud of points. So as time goes on, this cloud moves. And the mechanics. So you can, this phase space, 6-dimensional, that describes one atom is called mu space. Mu space describes one atom. And a gas of n atoms is represented by n points on this space. And it moves like a cloud. And our object study is not how one point moves, but how this cloud moves. There's another point of view which is more abstract and more general, which we'll come to later. It's called gamma space. Gamma space is the phase space of n atoms. So it is, since each atom has 6 degrees of freedom, it's a 6n dimensional space. And if I can, this is sort of p. This p is really n, p1 up to pn. And this is really x1 up to xn. It's 6n dimensional. And this whole 10 to the 23rd atoms is represented by 1 point. That 1 point specifies all the states of the n atoms. And as this moves, this point moves in gamma space. But that is an aspect that we'll come to later. Right now in kinetic theory, we are concentrated on mu space, on how this cloud moves. So our immediate object is to describe mathematically how that cloud moves. You know how this 1 point moves mathematically. I'm telling you, if you have n points, how do you describe how this cloud moves on the average? And that is the subject of kinetic theory. So now we will formulate how you describe this cloud. Now, as you suspect, you don't want to describe one atom. You want to describe the average property of n atoms. So what you want to do is not this one atom. You want to take a volume element here and regard this cloud as a fluid and see how this fluid flows in this space. In a way, you want to describe the hydrodynamics of that flow in this space. And therefore, you must first describe how do you describe the how do you introduce the object that would describe the system. And that is called a distribution function. So next, I want to introduce the important concept of the distribution function. A distribution function, as I said, describes the average property of the flow in mu space. So first we have to decide on how big is that volume element. That fluid volume element, how big is it? We have to first decide how to choose that volume element. The volume element in mu space. So in space, you have a cube, in momentum space, you have another q. You have dx, dy equals delta x, delta y, delta z, and then you have delta px, delta py, and delta pz. And so the volume x is equal to delta x times delta y times delta z, and the volume element in momentum space is equal to delta px, delta py, pz. We must choose this volume element so that it contains a large number of atoms. Must contain a very large number of atoms so that we can do statistics. But yet it has to be very small, but small enough to be considered a point to us. On our scale. It is because of this that we can do statistics. It is because of this that we can treat it mathematically in a continuous way. Is it possible? Is it possible to choose this? So let's give an example. Suppose you choose let's go to example. Suppose you choose delta x, the same as delta y, is equal to, say, 10 to the minus 3 centimeter. That's pretty small. Huh? You can hardly see it. So from our point of view, it's like a point. And yet, how many atoms does it contain? Then delta Vx would be equal to 10 to the minus 9 centimeter cubed. And the number of atoms in it will be equal to 10 to the minus 9 times the density that we just discussed before, which is 3 times 10 to the 19th. So this still contains 10 to the 10th atoms. 3 times 10 to the 10 atoms. So that even in such a small thing, which you can consider a point, it still contains 10 to the 10th atoms. So that's good enough for us. But you have to be careful about this, because consider another example. Suppose you choose another volume element with all the present emphasis on nanotechnology. Suppose that I choose this delta x as 1 nanometer. So we choose delta x is equal to 1 nanometer, which is equal to 10 to the minus 7 centimeter. And the number of atoms in that volume will be 10 to the minus 7 times 3 times 10 to the 19th. No, not 10 to the minus 21. You cube it. So you get 3 times 10 to the minus 2. So in that way, you only have 1/100 atom. So that's no good. You cannot do statistics with this. And that's why nanotechnology is on the borderline between classical mechanics and quantum mechanics. So when you work with kinetic theory and things like that, you have to be careful that your volume has to be large enough on the one hand to contain a large number of atoms, but on the other hand small enough so we can treat it mathematically as a point. The second probably is very important. Let me illustrate. This is how we define the distribution function. After having chosen a volume element, the distribution function is just chosen just by counting the number of atoms in that volume element at that space-time point. So now we have in our mu space at some point x and p, we have a volume element. So we call it tau. Tau is delta delta p, delta of vpx. We have this phase-space volume element here, and it has to contain a lot of atoms. And as time goes on, this moves. So it might move here. And this will be another point, x prime and p prime. And I would consider this point, but I would consider the volume about that point. And the distribution function is defined in the following manner. It is called f. F is a function of x and p and t. It is defined such a way that at this point, x, p, and t, you multiply it by d3x by delta vx and delta vp, and that is the number of atoms in that volume element. So if you know all the points in mu space, you count how many atoms there. At this point, you count so many, and that's f times the volume element. So f is the density, so to speak, the number of atoms per unit volume element. And then at another point, you move here, you construct another thing here, and you count. And if there are lots and lots of atoms, when you move a little bit, this function will be continuous. And that's an important point. We regard f as a continuous variable because of that. Regard this as a continuous. We regard f as a continuous function. And our object of kinetic theory is to find equation of motion for f. From classical mechanics. Once you found that, you can work out everything about the average property of the system statistically. That is, you derive all of thermodynamics. So we can see how this is done. So first, let us see how this f changes with the time if there are no interactions. Suppose you have a collection of free atoms. They don't interact. They just move freely. Then it's very simple because for free atoms, Newton's equation is very simple. So you know exactly how f behaves when there are no interactions. First of all, we know how that volume element changes with the time if there are no interactions, because that volume element has vertices defining the boundaries of that volume element. Each vertex is a point specified by x and p. We know exactly how that moves under Newton's equation. So we can see how that volume element moves when there are no collisions. Now, I need not work this out for you, but I think you will find that is the following result, which is eminently reasonable. Here's delta x. Here's delta p. How does this cube move under free motion? You have to work out how each corner moves under free motion, how it translates under Newtonian mechanics. After a while, it will move. It will not be a square. It will be a parallelogram, like this. See, under time dt. If you work this out, you will get the following result, which I think will be very reasonable. Now, I just tell you that this delta x becomes delta x plus the order of delta x squared. That is, to first order, it does not change. It changes to second order. And this is delta p plus order of delta p squared. And therefore, to first order, if we can treat these delta x as infinitesimals, to first order, the volume element does not change. This is an important one. Therefore, delta x, that is tau, which is equal to delta x, delta y, delta z times delta px, delta py, delta pz, is invariant under time evolution. In the limit delta x is equal to 0 and so forth. In the limit, you can treat each as infinitesimal. That doesn't change. So that's important, that the volume element is invariant. So now we consider how this distribution function changes. Since the volume element does not change, we can just concentrate on how the distribution function changes. Just imagine that, go back to this picture. Let's go back to this picture. Just imagine at a certain time you have this volume element, which contains a large number of atoms, and yet to us we can regard it as an infinitesimal mathematical quantity. Say A. A goes into B in time del dt, and B looks like this. So if there are no interactions, all the atoms in A will go into B in time dt. So if there are no interactions, all atoms in A will go into B in time delta t, infinitesimal time. And what does this mean? This means that F, since the volume element does not change, that means F of x and p and t, that's the number of atoms here, is equal to the number of atoms here, which is equal to what? Which is equal to F at x plus Vt, right? That's equivalent Newton, and P plus Ft, right? F is external force times T plus dt. And V, of course, is P over M. So this is the equation for how this changes. And if you let dt go to 0, you will say the F of x pt, you expand this in a Taylor series expansion, F of x pt plus d plus x is a vector, so it's a gradient with respect to x, f times dot vt dot v dt, x plus v dt, this is dt, I'm sorry, x times v dt plus gradient with respect to p, f dot f dt. And this is removed by dt, and this is removed by dt, and I cancel the dt on both sides. So the equation is, can I just write above? If there are no collisions, then you have these two cancel. So you just have d dt plus gradient of f dot p. So p over m is the velocity, p over m dot gradient plus f dot gradient with respect to p of f is equal to 0. This is the equation of motion for f if there are no interactions. Since f depends on x, p, and t, all this says is that the total derivative of f is 0. It's equal to this statement. And this describes how the free particle phase streams in this space. It's called streaming. Like a fluid streaming in hydrodynamics. This is streaming motion without interaction. But of course, we are not interested in a system without interactions. We're interested in the effect of interaction. The effect of interaction is to modify this equation. And therefore, we just write with interactions and what does interaction mean? It means collision. In the classical gas, the only form of interaction is when two atoms collide. They would move freely until they meet an atom that collide. So interaction means collision. So with interactions, this equation just becomes d dt plus p over m dot gradient plus f dot gradient of the p. F, all we need to do is this left hand side is not 0. So we just call it something. This is called df dt collision. This is a time rate of change due to collisions. And this is the definition of this term. And we'll construct this term. So this is the general form of the equation. And the task left is to derive what this thing is. And that's the crux of the matter. How does a collision affect the change of the distribution function? So now we focus our attention on collisions. And it's very simple. A collision, let me just say it in words. These volume elements are so small that if any atoms here encounter the collision, it will get knocked out of this volume element. So it will not reach B. So that means a decrease in the system. And again, if an atom found itself here, does not here, it must have come from outside. So the collision is to deplete or increase the number of atoms in this volume element. And we formalize this by defining some rates. The rate of increase in each of those volume elements during time dt, or the rate of decrease due to collisions. We will define those rates and then try to find an expression for them according to classical mechanics. But in this case, you will find that we need quantum mechanics. You cannot avoid quantum mechanics. So let R be defined as R times d3x. I now write d3x as the limit of a volume element when it gets raised with d3p and dt. This is defined as a number of collisions during the time dt in which one of the initial particles is in d3x d3p. If one of the atoms is in d3x and it experiences a collision, it gets knocked out. So that's the rate of decrease. And R bar times d3x dt is defined as the number of collisions during dt in which one of the final particles is in dt. So there's two things. And once you've defined that, then it is clear that the object that we want to find, df dt collision times dt, is equal to r bar minus r times dt. Therefore, df dt collision is r bar minus r. And all we have to do is to compute r and r bar from mechanics. And I think this is a good place to start for 10 minutes. Review something about collisions. And for this, we have to use quantum mechanics. You have to know it very precisely, but you have to know the notion. Why do we have to use quantum mechanics? Because of collision, you have two atoms coming this way. And each one is a wave packet, you know, classical, very nice. And then later they will go out. So this is P1, P2, and it goes P1 prime, P2. This is the momenta. But in between, the wave packets overlap. So in this region, you have to use quantum mechanics. Because the wave packets overlap. Once they overlap, they know that they're quantum mechanical. So that the process governing collisions is basically quantum mechanical, not classical. We describe the initial states and final states classically. But the collision probability has to be computed quantum mechanically. Of course, in many models, you use classical mechanics. That's an approximation. And that's what Boltzmann did a long time ago, before quantum mechanics was invented. But now we know that we have to use quantum mechanics. So let us describe a collision process in quantum mechanics. In quantum mechanics, you are talking about initial state and final state. And a final state. Called I and F. This I is represented by a quantum mechanical state labeled by the quantum numbers P1 and P2. These are plane waves. This is the Dirac notation to help you know what it is, but if you don't know precisely, it doesn't matter. It's just the notion of a state in quantum mechanics. So a collision is a transition between these two states. And in quantum mechanics, the object is to compute the transition amplitude between these two states. And a transition amplitude in quantum mechanics is called TFI. It's a T matrix and is given by a matrix element of a certain T operator between these two states. And that T operator is approximately equal to the interaction Hamiltonian in this so-called Born approximation. But there's an exact operator that gives you the exact transition amplitude. And we just assume that we know this. It's a complex number. And all this you have to compute using quantum mechanics. But once you know this, how do you calculate the rate of transition? So given an initial state I, you want to find out the rate of transition into the final state. So given a state I, P1, P2, you want to calculate how many transitions per second that occurs. So bring the system into the final state with P1 prime and P2 prime. But in all such problems, you have to be careful because the final state lies in the continuum. So you cannot ask what is the rate of transition into that one state. You have to ask what is the transition into a small volume element about that state. So the rate of transition I to F with Fn divided by P d3 P1 prime and d3 P2 prime. The final state has to lie within this volume element. And we call that probability of 1 to going to 1 prime, 2 prime. And it is a differential we call dp because this is a very small volume element. And this dp is given by, first, the volume element, d3 P1 prime, d3 P2 prime. This is just a volume element of the final state. And here comes the real thing, TFI squared. You take the thing you calculate from quantum mechanics, you take the complex conjugate multiplying squared, the square modulus. And there is momentum and energy conservation. So this is 4-dimensional delta function for the PF minus PI. PF is the sum of all the momenta. This is d4p is equal to d3p times the energy. Energy in P forms a 4 vector, and d4p is the product of the momentum part and the energy part. And d4, this delta function is not 0 only when the argument is 0. So that enforces momentum energy conservation. This just part comes from quantum mechanics. So, but this is general formula. So let me be more specific. D4 PF minus PI is first, this is a 3-dimensional delta function of P1 plus P2 minus P1 prime minus P2 prime. Conservation of momentum. And then delta function of E1 plus E2 minus E1 prime minus E2 prime, in which E is equal to P squared over 2m. And this is the threshold rate. When you find a cross section, you sum over. It doesn't infinitesimal volume element. When you sum over volume elements, that gets rid of the delta function. I'm sure you know all this in your course in quantum mechanics, but I cannot go into it here. But this is distinct advantage in our using this formalism here. You will see. So the number of particles that goes into let dn12 be equal to d3p1, d3p2. That's the volume element in the initial state. Let's put d3x. This is the initial state volume element. Times the probability of finding two particles with those quantum numbers x, p1, p2t. So f is a distribution function that finds simultaneously at x a particle with momentum p1 and a particle with momentum p2. So this is a correlation function. Because it's a two particle correlation function. So this gives you the probability of finding a pair of particles with initial conditions at x. First, you have to find two particles at x with momentum p1 and p2 at time t, and you modify the volume element. So this is the number of particles with the initial conditions. With these definitions, then you will see that R, let me write here. Now we can write down our rates R and R bar. R dt, which is equal to dt times dn12 dp 1 2 going to 1 prime 2 prime. This is the initial state, and this is the initial state make a transition to the final state. So R is the rate of transition to the final state, but we don't care about the final state because we only need one of the particles in the initial state. Therefore, you have to integrate over P1 and P1 prime and P2 prime. And I use the shorthand whenever I integrate with P. This is a shorthand for integral d3p. So you take this 1, 2. You don't care about what they are, so you integrate over both of them. And here you only need that one of the particles in this case, so you integrate with P1. No, integrate with P2. Then the result is in terms of P1. And R dt is equal to dt integral, again dn, but this kind 1 prime 2 prime times dp 1 prime 2 prime goes to the 1 2, the reverse, and then you integrate with p2 p1 prime and p2 prime. And with all this series of definitions, we have our result, because we have now expressed the rates which we want in terms of a quantum mechanical expression for the scattering. So if you, as long as you can compute that, you have the equation. So now let us put it back into the equation earlier and get our equation. Earlier we wrote down an equation for the distribution F with a collision term on the right hand side that is R bar minus R. Yeah. So therefore now the equation is df dt collision with something we want is just equal to R bar minus R, which is equal to the difference of the two things above. And now you can plug it into the equation, which is equal to before I write this down, I want to do one thing. No, I'll write that. This is equal to integral and we've got P1 prime, P2 prime, and P2. And the momentum on this side, the free momentum is P1 now, of delta 4 final momentum minus initial momentum times T Fi squared TIF squared F1 prime 2 prime minus TFI squared F1 2. For these two. Now I'm going to show that TIF is equal to TFI. That's very important. To do this, you have to realize some symmetries about two particle collisions. First of all, by time reversal invariance. This says that T of P2 prime, P1 prime from 1 and 2 is equal to the reverse transition, but with order momentum reverse. Is equal to minus P1 prime, minus P1, minus P2, T minus P1 prime, minus P2 prime. This is the statement of time reversal invariance. That is, the T matrix must have that property. The Hamiltonian must have that property in quantum mechanics. Therefore, this is true. But this is also equal to. But this is equal to P1 prime, P2 prime by reflection invariance. Because you change the sign just by reflection. Look in the mirror. And therefore, you have to. That is, the collision has the same amplitude as the reverse collision. And so I can factor this out. So now can I just use the eraser? I can just factor this out. Now we have not finished copying this. I'm going to erase it. With this, I have expressed the collision integral in terms of the quantum mechanical scattering amplitude times a two-particle correlation function. And this goes into the equation for the distribution function f. But you say that this question is not closed. I have merely expressed the time rate of change of f in terms of f, this called two-particle correlation function. And I don't know that. So that's the problem. So you say, okay, let us write an equation for f. So you try to run an equation for df dt. What is this equal to? Unfortunately, you'll find that this involves three-particle correlations. F of P1, P2, P3. That is, they're probably finding three particles at the same time in X. So, okay, no, I'll find dt for that. So, and for the df of 1, 2, 3 of dt depends on four-particle correlation. and so forth up to n particles. No, it doesn't stop. So it is hopeless if you want to include everything. You have a hierarchy of equations. The lower one involves the higher one until you reach n particles, 10 to the 23rd particle. But as in physics, when we encounter such problems, we make a bold assumption. That's we have to truncate the equation so to get a closed equation. And that's what Boltzmann did. In general, a two-particle correlation function, f of x, p1, p2t, can be written as f of x p1 of t times f of x p2 times t plus an intrinsic correlation. This is just the product of two one-particle correlations. In fact, in this case, the two particles are not correlated. They're independent of each other. It is in this term, that is, this term must approach 0 when p1 minus p2 approach infinity. This is a true correlation. This is the intrinsic correlation. This is just kinematic. It's just a term that you always have. So what Boltzmann did is that let us neglect this. And this is what Boltzmann assumed. Boltzmann has called this the hypothesis of molecular chaos. Anyway, to us, it is just known as a lack of correlation. You neglect the correlation. You neglect the correlation between two particles. And Boltzmann imagined the thing is so chaotic you can neglect it. But I think it's more accurate to say you just ignore the correlation. Once you truncate this, then you see that in this equation, f12 only depends on the distribution function, and the equation closes. You have an equation for f itself. And that's a Boltzmann transport equation. So let us now write it down. Once you have this, you have an equation for f alone, a closed equation for f alone. And let us write it out. Then you have d dt plus p over m dot gradient plus f dot gradient with respect to p f of x p1 of t. Call it p1 now. And this is equal to integral delta function pf minus pi t fi squared times f1 prime f2 prime minus f1 f2, and this is to be integrated over p2 p1 prime and p2 prime. The result is a function of p1, and this is what appears here. And this is called Boltzmann's transport equation. Now, you get this from quantum theory, or you got to assume something. And when you integrate this, you will get rid of the delta function. I don't want to carry that out because there's an advantage in keeping it in this form to display the symmetry of the equation. So unless you are really working on this equation, it's not good to carry out these integrations. Just leave it there for formal considerations. This is now the equation that will govern the kinetic theory of gases. All kinetic theory of gases is based on this equation. The left-hand side is kind of complicated. This is because it's a nonlinear integral partial differential equation. Rather complicated. And to this day, we work with this equation in hydrodynamics, and in magnetohydrodynamics, in all kinds of non-equilibrium situations. Now, when this was proposed in about 1860, around the same time as Maxwell's equation, Maxwell studied this equation by assuming a classical treatment of collisions. There was no quantum mechanics then. He sort of assumed that these atoms are hard spheres and they collide. And he tried to solve this equation, this historical node. I assume a force 1 over r to the n between atoms. And he works out the classical collision cross section with n. And he plugged it into the left-hand side and tried to solve the equation. He found that he could solve it if n is equal to 5. It's a magic number. Maxwell solved the equation at n equal to 5. Nonlinear differential. And that's the only exact solution we know. And the solution turned out in terms of a Sonnine polynomials. It's a kind of polynomial. It's like Legendre polynomials. It's a special kind of polynomial. If you expand f in Sonnine polynomials, then for f equal to 5, it truncates into a finite series. And Maxwell computed that, which is really to the force. And he found all kinds of computed all kinds of things like viscosity and all kinds of things like that. But we are more interested in the formal consequences of this theory rather than detailed computations. If you want to pursue detailed computation, the technique is to expand into Sonnine polynomials. You can have infinite series in general, but you try to calculate each coefficient. But we are more interested in the formal implication of this equation. So let us look at this equation. Let us look at that equation. The complicated thing is the right-hand side. Now, let us take a simple case in which there's no external force. So let us take f equals 0. So there's no external force. Then it is consistent to assume that the distribution function is independent of r. Then we can assume f of p and t independent of R. What does this mean? This means that in every volume element in space, you have the same momentum distribution. Every volume in space, independent of R. No matter where you are, you take a cube, and the distribution of momentum is the same. And then the equation simplifies, because then the equation becomes d dt, df dt is equal to, those two terms are 0, so we just get integral the collision is d4 pf minus pi times f2 prime f1 prime minus f1 f2. What is a property you want to find out? This equation, you would like to see, does it approach a steady state? Does this system approach equilibrium? Now, in equilibrium, df dt is 0. How does it come about? So, condition for equilibrium. First, it is sufficient that this vanishes. The sufficient condition is that f2 prime f1 prime is equal to f2 f1. For any collision, 1, 2 going to 1 prime, 2 prime, or the reverse. Any collision that has a non-vanishing cross section, for any the diffusion must satisfy this. This is sufficient condition. Why? Because when this is 0, then df dt is 0. That's clear, right? That condition, however, is also necessary. So that needs to be proved. That is, if this is 0, then this must be equal to 0. That's not obvious. You have to prove that. That's a necessary condition. That condition is also necessary. Is also a necessary condition. And the proof is due to Boltzmann. Boltzmann said, define the following quantity. Now we call it Boltzmann's H. H is a function of time. It is, by definition, integral of d3p of f of p and t and the log of f and p at t. That's his famous H. Boltzmann didn't mean it to be H. He means to be capital Greek eta. But the capital Greek eta is written as H, so it calls it H. So now the proof is very short. Once you define this, it's clever to define this. Once you define this, the proof is short. You just calculate dH dt. Just differentiate. The first time you get df dt times log f. The second term you just get df dt. you get you differentiate 1 over f in df dt. So it's just what you get. And so this is equal to integral d3p df dt of log f plus 1. Now, for log f, for df dt, you plug in the df dt from here. Substitute from earlier equation. You plug it in. What do you get? Then you get dh dt is equal to integral P4 P f minus pi T fi squared f1 prime f2 prime minus f1 f2. Times yeah, this is df dt, right? Times log f 1 plus log f2 minus log f1 prime minus log f2 prime. And we can rewrite this part as f1 prime f2 prime minus f1 f2 times log of f1 f2 minus log of f1 prime f2 prime. Now you will see that this quantity is always that not equal to 0. And this is just the structure. If this is greater than this, then this is positive, and then this is negative, and so forth. And this is equal to 0. dh dt is equal to 0 if and only if f1 prime f2 prime is equal to f1 f2. And therefore, this establishes that this condition is also necessary. That is, if this vanishes, that is, if df dt vanishes, then this must be 0. And therefore, this condition is both necessary and sufficient for equilibrium. Now, after all these formal manipulations, one should not lose sight of what is how do you say that in physical terms? What does it mean? It means that this condition is a condition on collisions. Given any possible collision, then the product of the distribution functions of the final state must be equal to that in the initial state. That is, this is necessary and sufficient for equilibrium. That is, in a gas in equilibrium, this condition is satisfied. It's a condition for equilibrium. And that determines the form of the distribution function in equilibrium. This also emphasizes the fact that equilibrium depends on collisions. It is collisions that makes equilibrium. You see, if you have a gas that has no interaction whatsoever, you put it in a box with reflecting walls, with arbitrary initial condition, they reflect back and forth within the walls. They don't interact. They never change. But equilibrium means that you have to change the velocities to a certain distribution. And that can only happen if there's collision. Even though there's a tiny amount, you must have it. And this emphasizes it. The equilibrium is due to a property of collisions. Now let us now look into further what this implies. How do we determine from this condition the form of the distribution function? If I take the logarithm on both sides of that condition, I will get the following relation. That is, the necessary and sufficient condition for equilibrium is that log of f2 prime plus log of f1 prime is equal to the log of f1 plus log of f2 for any collision in which 1, 2 goes in 1 prime, 2 prime. Now, this is a conservation law for a collision. Therefore, log f is any quantity that is conserved in a collision. Therefore, the general solution log f is any quantity conserved in a collision. Example, energy, momentum, angular momentum, if it exists, and so forth. That's the spin, and so forth. For our atom, without any inner structure, all we have is energy momentum. And therefore, for our case, log f is a linear combination of energy and momentum. Therefore, log f is equal to, say, minus alpha times momentum times some energy minus beta times momentum. Since there are 3 components, we have 3 coefficients beta. So it's just like, so this is the most general form of log f. And this gives you immediately f. Therefore, the equilibrium distribution function is of the form f is equal to some constant times exponential minus alpha e minus beta dot p, where e is p squared over 2m. In fact, why don't we just call it alpha p squared to save the 2m, because energy is p squared and you can absorb the term into alpha. So this is the most general form of the distribution function. Now we have to determine what alpha and beta are. Notice that that's a Gaussian distribution in the momentum squared, and then there's a linear term. But that linear term gives you an average momentum of the system. An average value, say the average momentum. This is equal to integral d phi p f of p times p times integral d phi p f of p. Now I don't need a t anymore because it's equilibrium. It's independent of the time. So this is the average of the momentum. And this should be equal to 0 for our gas, because if gas has no translation, it's equal to 0. And this then implies that beta is equal to 0. So if a gas has no average translational momentum, that beta is 0. So we just take that case. And therefore f of p and t is just equal to some constant times e to the minus alpha times c squared. Now we know what if we determine c and alpha. C can be determined by integrating over p. If I integrate the derivation over p, then what would be left is the density. F, in general, f of x, p, and t, if I integrate over d3p, the result is a density. And if I further integrate over the density d3x of n of xt, this is equal to n, the total number of particles. So now I can express c, I can find c by doing the integral. So now I integrate. Therefore, integral c d3p e to the minus alpha p squared, this must be equal to n. And n is a constant because it's equilibrium. There's no time dependent. Therefore, I can express c in terms of alpha and n. So let's do this integral. That's a Gaussian integral, and you can do that. Let me remind you how you do that. Gaussian integral. What does this mean? All this means is this. All this means is the integral dpx, dpy, dpz, each equal to minus infinity plus infinity, each one, of e to the minus alpha px squared plus py squared plus pz squared. That's what this integral means. And therefore, this is a product of three integrals, of three Gaussians. The most basic one is this one, right? Integral from 0 to infinity dx e to the minus lambda x squared is equal to square root of pi over 2 1 over square root of lambda. That's the basic formula that we'll use. Once you have this formula, you can differentiate both sides with respect to lambda and bring down powers of x. For example, if you take minus dd lambda on this side, you get integral 0 to infinity dx x squared e to the minus lambda x squared. And on this side, you differentiate with respect to lambda. You get pi over 2 times 1/2, 1 over lambda to the 3/2. So it's pi over 4. And you can even do integral 0 to infinity dx x to the 4th power of lambda x squared. It is e to the 4 times 3/2 times 1 over lambda to the 5/2. So it will be equal to 3 root pi over 8 1 over lambda to the 5/2, and so forth. So you can do all these integrals with an even power of x by differentiating that formula. And this is very convenient because now we can compute the average energy. The average energy is just the average of p squared over 2m, because p squared over 2m is the energy of an atom of momentum p. And so the average of the energy is just integral d3p times e to the minus alpha p squared times p squared over 2m. integral d3p e to the minus alpha p squared. Now you need a p squared with 2m here, but this d3p, well, you can figure this out, right? This is a sum. P squared is a sum of px squared, py squared, pz squared, and so forth. I will not bother to do the algebra. From this one, you can easily find. That the result is 3 over 4m alpha. So now we know what C is. We have expressed alpha in terms of the average energy, and that solves the problem. We will later show that this is 3/2 times kT. Okay, it's a temperature. But to relate it to a quantity that we can measure. But that would be, to do that, we have to compute the thermodynamics of the system. But right now, we have everything. So we have the Maxwell, this is called the Maxwell-Boltzmann distribution. Which is the distribution of a gas in equilibrium. It only depends on P, assuming that there's no external force, is equal to C times e to the minus alpha p squared, where alpha is given by, related to the average energy by this formula. So it's a Gaussian. And usually you plot, usually you want to plot f squared times p and t. You usually plot that against function p, because the in momentum space this particle depends only on p squared, and the shell of p squared is of area p squared. So when if you don't have this term, it's a Gaussian, but if you have this term, you get something like this, which means that there's an average momentum here, and this is width, and this will contain all the properties of the thermodynamics of the system, and we will take it from here and derive all the thermodynamics of the system, and plus more, we can derive all the hydrodynamics of the system, and then we have a complete picture of how a dilute gas can approach thermodynamic equilibrium. I think we'll stop here.